I think so. Okie doke. Good morning, my name is Feike Leij, very difficult name. I have a Dutch background and I've been doing research in subsurface water flow for about 30 years. And the last 10 years I've been a lecturer at Cal State Long Beach as well, teaching classes such as fluid mechanics, statics, a little bit of hydraulics, and graduate math and groundwater flow classes. So today we're going to cover fluid mechanics in the morning, maybe a little bit this afternoon, and then we will do hydraulics and hydrology. Now, fluid mechanics is a very fast subject, so I want to use our time wisely. And I assume that the material is familiar to you. If not, we can start delving into it. So we kind of skim through the manual, and then after that we're going to solve problems, maybe some tips to speed up the problem solution process. That sounds fair enough? And I understand we also have somebody in Illinois. Can you communicate with us, ask questions? Okay.
Yeah. So she can talk.
So this is all new to me. You have to be a little bit understanding. I'm not quite up to speed with the technology compared to some of the other teachers. But together we will make it a worthwhile experience. So let's start with the properties of a fluid. A fluid, unlike a solid, has some distinct properties, and you probably recall that the lack of a fixed shape, and for a gas, even a fixed volume. So there's some terminology here, the density. That should be familiar, Greek letter rho. We don't use that as much as in other solid mechanics classes. Mass divided by volume. Especially for gases, we may use the specific volume, the inverse of the density, the volume that's occupied by a unit mass of the gas. And that's of interest because gases expand, can take up a large volume. Probably the more important variable is the specific weight. Yeah, the weight density in a way, for which we use the Greek symbol gamma. And the weight is related to the density using the gravitational acceleration, rho times g. So here's the example. As we know the density of the gas, we can get the specific weight by multiplying it by the gravitational acceleration. It's good if you have some idea what the number should be, and I've seen more than one person being tripped up by using the incorrect value for g. And so we unfortunately need to be able to use both US units, 32.2 feet per second square, and SI units, 9.8 meters per second square. So the units for gamma would be either Newton per cubic meter in the SI system or pounds per cubic feet in the US units. Then for liquids, we like to use the density and the specific weight of water as a reference. So for an unknown arbitrary liquid, the ratio of density of that liquid with respect to the density of water is the specific gravity. Yeah, since gamma, the specific weight, is rho times g, yeah, these ratios are really the same because gravitational acceleration obviously is not going to change. This is all familiar to you. Should we speed it up a little bit? Speed it up a little bit. Yeah, then pressure. Normally in fluid mechanics and hydraulic, we use gauge pressure, the pressure with respect to the atmospheric pressure. Yeah, our system is typically under atmospheric conditions, so there is no point in including the atmospheric pressure as a reference point. So the gauge pressure is the absolute pressure minus the atmospheric pressure. The absolute pressure, which you use, say, in thermodynamics and physics, the ideal gas law, is therefore the sum of atmospheric pressure and gauge pressure. Some values to keep in mind: the atmospheric pressure in the SI system is 101.3 kilopascal, or US units is equal to a column of mercury of 29.921 inches. Here are some typical values for water. Depending on temperature, the specific weight. This would be in kilonewton per cubic meter. The density, the dynamic viscosity, the kinematic viscosity, and the vapor pressure. Do we recall the relationship between dynamic and kinematic viscosity? Mu and nu, the Greek character for kinematic, how are they related? By the density. Mu divided by rho, the density gives the kinematic viscosity. Mu has units mass over length over time, and kinematic viscosity has units of length square over time. Now for liquids, the viscosity tends to decrease with temperature. Yeah, engine oil, if you heat up the temperature, the viscosity diminishes. For gases, a little strange, it's just the opposite. The viscosity increases because of greater molecular movement. So we're familiar with absolute and gauge pressure. Do we need to look at the number example, or we can do this? I take it that you went through some of this material before you came here. Skip it. Then very closely related to pressure is stress. Yeah, force per unit area. Unlike solids, liquid cannot normally support a shear or tangential force. So for an ideal fluid, you will not have shearing. The normal stress is related to the perpendicular force. If the fluid is at rest, that will be the hydrostatic pressure. That's stress, force divided by area in this way. If there is any change in velocity perpendicular to the direction of interest, yeah, so-called tangential velocity profile, then we can figure out the shear stress based on the viscosity of the fluid. If we have a Newtonian fluid, the shear stress, this force along the direction of perpendicular to the direction of flow divided by the contact area is the dynamic viscosity multiplied by the change in velocity perpendicular to the main flow direction divided by the perpendicular distance. Fa is that shear stress tau. So V is a function of the perpendicular distance y. This is the transverse velocity gradient. So the shear stress for Newtonian fluid is going to be proportional to this tangential velocity gradient. Mu, what is that again? Dynamic viscosity is the proportionality factor. Now, not all fluids are Newtonian. For example, paint, certain starches, they start to react differently depending on the shear stress, and we don't have a proportional behavior. Now, in fluid mechanics, for civil engineering and mechanical engineering, we typically not too worried about it. We often assume Newtonian fluid, but for the folks that are, say, in chemical engineering or dealing with food, they really have to pay attention to non-Newtonian behaviors. If this power is less than 1, we have pseudoplastic fluid. If it's greater than 1, we have a dilatant fluid. I wouldn't expect too many questions about this though. And I mentioned the relationship between kinematic viscosity, mu on the left-hand side, and the dynamic viscosity, mu, so you divide by rho. This kinematic viscosity is somewhat related to thermodiffusivity and molecular diffusion, how soon the stress can be evened out. Then we look at the next fluid property, surface tension, unless you have any questions about viscosity. The surface tension occurs at the interface of different fluids. Normally, it's not a consideration, but if you have a confined area, for example, a straw with water and air coexisting, then there's going to be some curvature. The membrane, the interface between air and water, is going to be warped because the forces within the water, between water molecules, are going to be different than the force between, say, water and air, and the force between water and the solid of the straw or the capillary cylinder. Water happens to be a has very weak cohesive forces, so it likes to wet other surfaces. So if you put a capillary tube in a water reservoir, you will have a capillary rise. The coefficient of surface tension is denoted by sigma, and it's equal to the force per unit length of contact between the two fluids. So sigma has units force over length. In the SI system, Newton per meter. Because the values are so small, it's often also expressed in